2 lectures and discussions. All right. And then also next week we will have invited speakers. Tuesday and right? No. Thursday and then also the other Tuesday. So for the invited lecture, please come to the lecture room so that they are pleased to see your faces. And then also I have contacted CRISO. CRISO is a research institute not far away. And we will have a trip to CRISO on Friday afternoon between 12:30 to 3:30. Then I need to know about how many of you will participate. So please vote on this link provided by the TA. So let me know whether you are coming or not coming, so that I can contact Chris or how many of us will come. Any other questions? No questions. Then I can continue my part of the presentation. So this is the hydrostatics, not dynamics. So this is the textbook we are covering, and then chapter 6 is statics stability. And my part will be the buoyancy and fluid mechanics, pressure, and something like this. So we start with the solid and fluid. What is the difference? Solid may be deformed by an external force. However, its shape does not change indefinitely. So soft material, or not so soft, may bend, and something like plastic. We can apply force and a little bit change, but it is still solid. So I may say we already study about what is topology and geometry. Did I? Topology and geometry. Did I explain this one before? No? No. Topology and geometry. Because we studied about nerves and surface as a shape geometry, I may not explain this one. All right. Do you have any eraser made of soft material of eraser? Somebody? If I draw a grid on top of the soft material of eraser, and then if I twist them, the shape can be changed, and then also the grid may be distorted. Right? On top of the eraser, golf eraser, I make a check box or grid, and then twist them. Right? And topology, any geometry of mathematics is made of topology and geometry. And topology is something like a neighborhood information. Neighborhood means on my right hand side, who is there? On my left hand side, top of them, bottom of them. So the grid, you have the neighborhood information is there. Right? A box, a square, right hand side, left hand side, top, down, it's clear. Right? Even if I twist the soft material, the neighborhood, the topology does not change. Topology is the same. The neighborhood information is the same. but we say geometry is changing. Geometry is changing. But when I twist that soft material further and further and further, in the some period of time, it can be departed, break down. Then we may say that topology also changed. The neighborhood information is breakdown. So topology and geometry is a two important property of mathematical geometry of shape. Once again, back to your solid. The solid can be deformed, right? Soft material also. However, shape does not change indefinitely, even until they break. If they are not breaking, but fluid cannot resist any deformations, small deformation forces, the shape will change continuously. Like water, any force make them change their shape. No topology, no shape, no geometry. So that is the main difference between solid and fluid. And fluid is a bigger concept than liquid or water. So liquid and fluid is not same. So fluid is bigger concept than liquid. Liquid is one part of fluid. And also there are gas. So in aerospace, who is the aerospace department here? Right. Oh, aerospace. Aerodynamics is most important thing in aerospace engineering. For shipbuilding, water dynamics is fluid dynamics. Aerodynamics is less important, but they are very similar. So gas dynamics is here, and plasma and plastic solid is also. So density, you already know in your undergraduate studies or high schools already, but we remember is a density of fluid, low definition, mass per unit volume. So it's a mass divided by volume is a density. The unit is kilogram per cubic meter, affected by change in temperature and pressure, especially for aerodynamics. The density is changing. But for the fluid dynamics, we can assume that it is not changing. There are more changes, but can be negligible. Based on temperature and pressure. Water change is very small, so we can neglect the change affected by temperature and pressure. Typical values: air is small, and fresh water, seawater, so that the ratio is about 800 times. It gives you very big difference in physics. Pressure is definition by force per unit area. So force is something like a weight. So as I told you before, that air pressure here, air pressure is the weight of the air above me. And similarly, the water pressure down to the water, there is a weight of the water at that point. So we say that every 10 meters, the same amount of air pressure is increased every 10 meters of water depth. So weight is made of similar weight pressure. Pascal and bar for the air pressure. Something is miswrited here, something like that. Correct. The standard atmospheric pressure is 1 bar. 1 bar here. Okay. Is about. Right? And pressure in a fluid is density, gravity constant, and height of the height is equal. It is same as the weight of the water overview at the depths. And viscosity, measure of resistance of fluid which is being deformed by either shear stress or tensile stress. So it looks like honey or other grease. We call this a thickness in everyday terms. Water is thin, honey is thick. So that is a kind of viscosity in lifetime, everyday life terminology. And liquid and gases. So the pressure is a force per area. It's quite different because change of volume is compressibility. Compressibility is change of volume based on pressure. So it's a derivative of volume comparing to the pressure change. But water can be assumed to be incompressible. So it is actually 1.1% volume under 20 bar pressure. 20 bar means 200 meter water depth. 200 meter water depth. Very high pressure, right? And 20 bar. But volume change is only 1,000th of it. So we can negligible the compressibility. But aerodynamics, compressibility is very important. So hydrodynamic and aerodynamic is a difference. Similar, but quite not same. Density change is the most important, and also compressibility, and also free surface. There is a free surface. Free surface is a surface between air and water. Free surface. That gives you a very different changes to never, especially the wave. Wave is only for free surface. But also you can observe some free surface effect or wave, something looks like a wave in aerospace. So similarity, right? Shape is similar, not the same, but very similar. And also you see that the propeller is different. Right? For the water propeller, for the air propeller is different because of the density, big density change. Pressure in a static fluid. As I told you before that water depth is proportional to the pressure there. So that you see that you expect that pressure is higher in the lower part. So pressure increase with the depth. Pressure act at a point in all direction equally, right? This one, right? And also perpendicular to the surface. Perpendicular to the surface. Perpendicular to the surface. Perpendicular to the surface. Actually, this one is not correct. Because of the size of the bubble, there should be a small difference in pressure. So at single point, no size, then all direction is same. With some size, if you are saying this size can be 10 meter diameter, 10 meter means 1 bar difference of pressure. 10 meter. So if this diameter is 10 meter, large of that diameter, then the pressure here and here can be 1 bar difference. And then also you can expect that pressure at the top is small and then increasing as water depth is increasing. So then you need to have a thicker plate, steel plate in the bottom of the ship compared to this. But it is only for the water pressure. But there is other forces coming to the steel structure. So it is not so simple. But anyway, if you are thinking about only water pressure, it can be thinner than thicker. But in their ship, also the bottom plate is thicker than the side ship. Not the same proportion with the water pressure, but there are differences. Hydrostatics. Statics means no dynamics, no time change, no time change. So buoyancy is a static wording applied to an object, so that there is a volume of water at the equilibrium. You see that there are pressure differences. And then integral of whole surface, not only the circular line, but also the whole surface of sphere. Then you can have a area integral of pressure around the area of the surface. Then we arrive at this is the force, total force coming from the water to the solid. And then depending on the inside, what is inside the ball, then the ball can be floating or going down or neutral there. Submarine, it can be a submarine. So buoyancy is once again the forces of all the outer pressures integral of the surface, forces. So pressure, integral of them. But because the size is different, so that there should be a net force supporting the body. That net force we call this is a buoyancy force. And that buoyancy force is the same as the equal volume of water there. Displaced water. If there is no body, water was there. But because of this solid one, the water of this amount is displaced. And that amount of water, weight is same as the displacement or the forces, the buoyancy force. We already told you several times. So there is a upward acting force. This one. But this one is coming from the integral of all the pressures, balanced by the weight of this object, the gravity. So this can be a ship on the water surface. And then the total weight should be the same as the buoyancy, so that that ship is not moving, static. Equilibrium, force equilibrium between water pressure, buoyancy, and weight of the ship, the gravity force. So weight of displaced water should be, we call this is the displacement. So it is very natural and very simple, looks simple, but it can be complicated when you calculate something as a ship design, because ship is big and complex. But basic physics is very simple. Submerged body means submarine. Fully submerged, it can be neutral, but it can be floating. So partially submerged, floating. So if you want to be a commander at the submarine, then how can you manage your buoyancy of your ship or submarine? By controlling ballast water tank. So it can be a neutral displacement or buoyancy, or it can be somehow less buoyant, bigger buoyancy, so that it can float above the water by controlling the water tank, ballast water tank inside by using pump. Right? And iceberg, only the tip of the iceberg is above water surface, depending on the density of the ice. Or your body is also, I told you before that your body is very similar to iceberg. If you have your lung is full of air, you are floating a little bit similar to iceberg above water. Submarine, how to dive and surface. Deep dive, so that on the surface, on the water, there is a water tank. Water tank is outside of the main hull, and then they are full of water there. So the ballast water is filled, not all of them, but theoretically there is a change. All right, so there is a video. Let's see.
They can reach depths of about 800 feet thanks to a system of internal and external ballast tanks.
We have 5 external ballast tanks that are normally filled with air when I'm riding on the surface. When it is time for us to dive, we'll open vents on those ballast tanks. There's grates on the bottom of the ship that allow water to come in, displace the air, making the ship just slightly negatively buoyant. We then proceed down to the depth that we want to go to. And we use internal ballast tanks to make the ship neutrally buoyant, that then we can progress on our way in whatever depth we choose.
The crew on board the Virginia class have an abundance of cutting-edge controls at their fingertips, one of which is replacing the most iconic feature in submarine history. The periscope has been a key component on the submarine for over 100 years, but engineers on the Virginia class are taking a bold step toward the future by replacing the periscope with a state-of-the-art photonic mast.
The photonic system is a mast with a sophisticated camera system that allows what would normally be displayed just in a periscope to be displayed on widescreen monitors throughout the ship.
And I used to have an optical periscope that came down, which drove the construction of the submarine and the orientation of all of the rooms on the submarine.
Bulky periscopes force most submarine control rooms to be located on a cramped upper deck. On the Virginia class, the compact imaging equipment is housed in a part of the submarine known as the sail. This allows the sub's control room to be built on the wider second deck.
My control room that I'm standing in right now houses all of the important decision makers. It really brings the crew together to operate as a team, as a unit.
레드 좀 했어?
Question? No. I'll continue. Stability. There are 3 states of equilibrium as a theory: stable, neutral, and unstable. And there also it comes with a disturbance. Very small disturbance is coming. So when there is a small disturbance on each state, stable system with applying of disturbance, something like a wind, or something like a vibration, earthquake, stable system return back to the original position, right? Neutral, they stay as much as moving. But unstable one, if you have a small disturbance, it falling down, right? Something like this one, disturbance. So ship stability is the same theory, right? So we need to have a stability index for the ship because ship is moving in very rough water area, storm area, big wave and high wind. So that stable enough, then the ship can survive. Otherwise, even though the water is stable, not so big storm is coming, but ship can capsize even with the very small disturbance. Same theory as before. Ship stability, then how can you, as a ship designer, how can you design a ship with a good stability? Ship is statically stable, but see that, statically stable and then dynamically stable. There is another word. So we will see on Thursday, but now we are saying statically stable. Float upright when at rest in still water. Still water means there is no wind, there is no wave. It should be upright and return its initial upright position if there is a slight temporary deflection to side by this kind of which is called the disturbance. Say it can be a wind, it can be a wave, disturbance, or can be a movement of some people. If you have a chance to ride a very small boat, you can capsize your boat. Because comparing to the ship, your body weight is big. But for the big ship, your body is negligible. Your movement is not so. 저것도 같이 되는 거야?
아닙니다.
이거는
둘다 빨리 되다.
그렇게 되는 거 어딨으면. 자, 합시다. Let's go on to lecture by who is it? 박시영?
네,
Let's go ahead.
I will introduce more concepts about hydrostatic stability. First, I will introduce the concept of metacenter. Typically, the vessel's center of gravity is higher than its center of buoyancy. When a stable vessel is tilted, the volume displaced is larger in one side. Gradually, the center of buoyancy shifts towards the same side. The vertical line through the new buoyancy center will intersect the ship's center line somewhere above the center of gravity, which is termed as the metacenter of the body. An analogy can be made with the rocking chair. As the rocking chair moves, the center of support, which corresponds to the center of buoyancy of the ship, also moves, keeping the chair from tipping over. Also, we call the distance between the center of gravity and metacenter as the metacentric height, GM. We can determine the stability of the ship by checking the sign of GM. If GM is positive, the ship is stable, and if GM is negative, the ship is unstable. We can assume GM is nearly constant for small heel angles. In addition, we call the multiplication of GM and the sign value of heel angle as the riding arc, GZ. Let me show a video explaining concept of GM and stability.
사운드가 안 나오는 것 같은데, 사운드 없는 거예요?
아니요, 잠시만요.
예, 저 화면 공유를 중지했다가 다시 들어오세요.
네. 들리시나요?
네.
And if the weight of the fluid is less by this,
뭐가 또 끊겼는데?
body is known as the metacentric height, GM, which is given by, depending upon the location of the metacenter, a floating body possesses three types of equilibrium. They are stable, unstable, and neutral equilibrium. When M is above G, then in this case, a restoring couple is formed by the buoyancy force and the weight of the body, which tends to turn the body to its original position. Thus, the body is said to be in stable equilibrium. Now, when M is below G, then in this case, an overturning couple is formed by the buoyancy force and the weight of the body, which tends to sink the body from its original position. Thus, the body is said to be in unstable equilibrium. And when M coincides with G, then in this case, the line of action of buoyancy force and the weight of the body are collinear and passes through the same point. Due to this, the body neither returns to its original position nor increases its displacement further. Thus, the body is said to be in neutral equilibrium. Metacenter.
The computation of GM is made as following. There are three terms involved. First, KB is the height of the center of buoyancy above the baseline. BM corresponds to the moment of inertia of water plane area divided by the volume of displacement. Kg is the height of the center of gravity above the baseline. GM is computed by the sum of KB and BM and subtraction of Kg. The actual GM can be found by the experiment of inclining experiment. Let me show you some video.
Hello, in this video we're going to be exploring the inclining experiment. So the inclining experiment is typically done to determine the kg of the vessel. It can be done for the light ship of a vessel. Typically it's done for the light ship after a new build or after some kind of modification in a maintenance or yard period. The basic idea here is that you have a known weight. You might load it up on the center line. And on the ship, you will hang a pendulum. And you'll know exactly how long that pendulum is. And down at the bottom of the ship, you're going to set up, a kind of a wooden batten down there. Okay? And that pendulum will have a plumb weight on it. And then what you'll do is you'll take that weight. Okay, you'll know what the weight is, and you'll slide it a known distance to port or starboard. In this case, if you're looking at it from astern, the weight was, they slid the weight a known distance, okay, from center line to starboard. And what happens then is that pendulum is deflected, okay, it's deflected a certain distance, and you can actually measure it on the batten. You can draw a line there. So you have a line drawn for the center line, and then you have a line drawn after you've inclined it with a known weight and known distance off the center line. And now you have a deflection. And there's a ratio of the length of that pendulum and the deflection. And that we can relate that to this angle theta, which would be the angle of list created by that off-center weight.
If an internal liquid exists, it will flow along the direction of healing. This will eventually reduce the metacentric height. Since it changes the center of gravity, cm. This effect is called the free surface effect. This will increase the danger of unstableness, which will lead to capsizing. However, free surface effect is neglected if the tank is completely filled with internal liquid. The range of stability can be expressed by the relation between the angle of heel and the riding arm. The heel angle at which the riding arm crosses zero is an inclination where the vessel stability changes from positive to negative. The longitudinal stability must also be considered. A ship rarely capsizes in the fore and aft direction. However, the trim change by adding or removing weights on the ship in the longitudinal direction is also an important concern. When a hull is in damage, flooding occurs, which increases the instability of the ship. Once a compartment is flooded, the buoyancy provided by that compartment will be lost. Then the ship will sink deeper and its longitudinal center of buoyancy will usually move and cause trim. Here, we introduce the concept of intact stability and damaged stability. Intact stability refers to the stability of a vessel in its undamaged condition. It deals with the vessel's ability to resist capsizing or rolling excessively due to external forces such as waves and wind. Intact stability calculations take into account factors like the vessel's geometry, center of gravity, buoyancy, and moment of inertia. Damaged stability, on the other hand, focuses on the vessel's stability after it has sustained damage or flooding. It assesses the ability of the ship to remain afloat and maintain stability even with compartments flooded or structural damage. Damage stability calculations are crucial for evaluating a vessel's survivability and ensuring it can withstand damage scenarios. These calculations consider factors like the extent of location of damage, free surface effects, and redistribution of weight and buoyancy due to the damage. A bulkhead is an upright wall within the hull of a ship to increase the structural rigidity of the vessel and create watertight compartments that can contain water in the case of hull breach or other leak. A ship should satisfy one compartment standard, which requires that at least one compartment bounded by watertight bulkheads must be floodable without sinking the ship. Other than ships, stability of submarines is considered in circumstance when it is fully submerged and partially floating. First, when the submarine is floating, the mechanism of stability, which is called the surface stability, is same as the surface ships. When it is totally submerged, the PM term is neglected since the center of buoyancy does not move. Then, the stability is determined by whether the center of buoyancy is above the center of gravity. I will show you some video.
Looking at the differences between ships and submarines. Firstly, most obviously, there are huge implications in terms of buoyancy and stability. With a ship, you just need to make sure the underwater part of your vessel displaces enough water to provide buoyancy to keep it afloat. Submarines, of course, are a little different. On the surface, just like a ship, the hull needs to displace enough water to provide positive buoyancy, but it also needs to be able to sink, so you need to be able to increase its displacement to make it weigh more than the water it displaces. It's actually quite simple. You just flood some ballast tanks, making the vessel heavier and less buoyant, basically so that it sinks. That's great for going down, but then when you're deep enough, you need to be neutrally buoyant instead. You want the submarine to weigh the same as the water it displaces, so that it neither floats nor sinks. Again, it's quite simple, you just pump out a little ballast water using compressed air from cylinders. Done precisely enough, you can make the submarine weigh the exact same as the water it displaces, making it neutrally buoyant. So, that deals with the buoyancy, but what about stability? After all, a submarine still needs to remain upright when underwater. Remember how a ship uses form stability to stay upright? This just means that the shape or form of the hull provides a righting force whenever the ship leans over slightly. The underwater shape changes, shifting the centre of buoyancy, separating the force vectors, creating a moment to right the ship. This is how, counterintuitively, the centre of gravity can be above the centre of buoyancy. A submarine, however, can't do that. When it's fully submerged, its underwater shape remains constant no matter how far it leans over. Its centre of buoyancy doesn't move. Instead, you have to rely on keeping the centre of gravity below the centre of buoyancy. Your stability is provided by the force of gravity and the force of buoyancy pulling in opposite directions. Underwater, it's easy because you just make sure the heavy things are placed low down, but on the surface it can be a little harder. Think about it. As the hull emerges from the water, the centre of buoyancy drops lower down because it's just the centre of the underwater volume. If you let it drop too low, it might go below the centre of gravity and the submarine would just flop over. This is why submarines appear to float really low in the water. They need to keep the centre of buoyancy above the centre of gravity. So, we've now dealt with buoyancy and stability, but what about navigation? We already said
Thank you for listening.
Questions being? Okay, move on to the discussion session. Helen? Look at this. 화면 공유해야 되는데. 이따가
Okay. Hi, I'm Song-Hyun Yoon. I will discuss about the ship hydrostatic. First of all, to remind what we studied today for a meta center, the vessel of the ship, center of gravity denoted as G should be higher than the center of the buoyancy B, like in like G and B. And for the floating body, the angle of tilt, which means the ship, the vessel tilted. So the angle of the heel causes the center of buoyancy to move to sideways, like here. Actually, when it's upright, the B1 was the original center of buoyancy, but as the ship is tilted, the center of buoyancy moved to B sideways to the B2. Then previously we studied about the chair analogy about this stability. So anyone can fill in the blank A, B, C with these, and whether this chair is stable or not. Okay.
A is center of buoyancy, and B is center of gravity, and C is meta center.
And
it is stable because the meta center is above of center of gravity.
okay, yes, it is correct because as he mentioned, the A is center of buoyancy, and B is center of gravity, and the cross point of the line is the meta center. Then, as he said, it is stable because the meta center is above the center of gravity. For the free surface effect, when the ship tilts to one side to make it stable, there is some liquid in the ship. So the liquid flow to the same direction, and this raises the metacentric height, reducing the metacentric height, which means that the ship has a better stability comparing with the with the free surface effect and without the free surface effect. So okay.
Hello everyone, welcome to our e-learning classes for naval architecture. Hope you guys are doing absolutely fine, and today we are going to talk all about one of the most prominent phenomena regarding ship stability which ever takes place on board: free surface effect. The moment we talk about liquids, they have a tendency to flow since their weak intermolecular force allows them to do so. It simply means that liquids may acquire any shape they are kept in. As all of you must be knowing that a ship carries number of liquids in its various tanks for the purpose of its own operation. Everything in or on a vessel has its own center of gravity: the engine, the anchor, the ship's hull itself, your batteries, the cargo, and of course the liquid in your tanks. According to the weight and location, everything aboard contributes to the position of vessel's overall center of gravity. Heavier things influence the position of center of gravity more than light things. Off-center weights can pull center of gravity off the center line, causing the vessel to list. List means a permanent transverse inclination acquired by the ship. Let us now arrive on the concept of free surface effect. When a tank on board is not completely full of liquid and the ship is, the liquid moves in the corresponding direction of vessel's inclination. Because of this, the center of gravity of ship moves away from the center line, which reduces the righting lever and also causes a virtual reduction in metacentric height of the ship. When in calm conditions, this is how liquid surface looks like. Representing the same on a two-dimensional plane would give us this. Ideally, we can assume it as equivalent to a straight horizontal line. In all of our upcoming diagrams, waterline will always be shown with a straight horizontal line. Since we are talking all about transverse stability of the ship, let's have a look on cross-section of the ship. The ship being floating on waterline WL, it is consisting of a partially filled tank inside. Because of some external forces, the ship will now heel in a particular direction. The liquid within the tank would also be shifting in the corresponding direction of vessel's inclination. The transference of a liquid from one side to another takes place in the form of some triangular wedges, the wedges being called respectively as immersed wedge and immersed wedge. Just by looking at this diagram, I hope you get to understand why it is called as the immersed wedge and this one as the immersed wedge. Since a considerable liquid's mass has been shifted in a particular direction, this will also be causing center of gravity of the ship to move correspondingly in the same direction. Gravitational weight of the ship will now be acting downwards through new center of gravity G1. If we extend this line further upwards, this would be intersecting the center line somewhere. Now this vertical line makes an angle with the center line, so-called angle of heel. This is theta. The ship has been assumed as floating with a displacement delta. Since your ship's hull may have a complex curvature throughout its length and breadth, that's why it is useful for us to take into consideration a small strip of the tank lying at a particular section, the length of that strip being dx, which is very small. Let us now have a look on geometrical dimensions of the tank. It is consisting of a half breadth of y. The center of gravity is of immersed, and immersed wedges are lying at 2/3 of y, measured from the tank's center line. Some more dimensions can be seen here. Just like this, we have as equals to y tan theta. Since the angle between initial and final waterlines, which we have here, is theta, shift in center of gravity, that is G1, is well determined by dividing moment of mass with the ship's displacement. So first we will be determining the liquid's mass in that particular wedge, and then we will be multiplying it with the respective distance covered by its center of gravity. To do so, first let us have a look on cross-sectional area of that liquid wedge. The area of this liquid wedge will be well given by half of base into height. It is simply half of y into y tan theta. Volume of that small strip having length dx will be further given by, like, we will multiply it with 1 dx here. Further simplifying, it gets changes to half of y square into tan theta into dx. Now, how much will be the mass of liquid contained in that small strip? We will simply multiply this volume with the density of liquid which is being contained inside. The density being rho here. Now, we are arriving on the moment of transfer of strip of wedge. Apparently, this liquid wedge is getting transferred on the other side, and distance covered by its center of gravity in the upward shift direction is 4/3 of y. Let us just multiply the liquid's mass with this distance here. Simplifying further gives us rho into 2/3 of y cube into tan theta into dx. This expression gives us the value of moment of transfer of strip of wedge, means that small strip. In case we want to determine the moment of,
There are so many mathematics. So to sum up, actually it shows that the buoyancy level, horizontal is supposed to make the better, to have better GB. So yes, the right moment is a moment which makes the ship to make it upright when it's killed. What will happen when the angle of hills it gets increases? Or in terms of right moment, the change of the right moment and the angle of hills. Okay.
If I move over hill increase, the right moment increase until the neck angle leading to noise.
Okay. Anyone? Nope. Okay. As seen in the graph, here as the angle of hills increases, at some moment the right arm increases, so the right moment gets increased. But at the maximum point, when it reaches the maximum point, then the right arm gets shorter, which makes the range of the stable writing moment to the less writing moment. So when the until to get this point, the writing moment is pretty large, so it can be stable. But when it's over some point, the writing moment gets small, but it still can be stable. But after the zero moment, it will have after the zero moment, it will get negative, so it will be capsized. For stability of submarines, submarines are submerged vessels, so it has two stability: surface stability and submerged stability. As we studied about the surface stability, when the submarine gets to the surface line, it is governed by surface stability. But when it's submerged, when it's underwater, it is governed by submerged stability. So what happens if G is above B for submerged body, and why? These are for submerged body. Okay.
The submarine will not stay still and will just float.
Yeah. For submerged body, the height of metacenter is same as GB. GB should be positive to be stable. GM is the height of metacenter, and for submerged body, is the same as GB, so GB should be positive to be stable. Therefore, the case A is stable, whereas B is unstable. Yes, this is all. So thank you.
It will be on Thursday as usual, but there will be no mic lecture. 3 of you will have 2 lecture and 1 discussion. Any other question? No, then we can see on Thursday here. Bye now.